All right, section 5.4, exponential functions. We're going to look at differentiation and integration in this section. But to start with, just to define what we're referring to when we talk about a natural exponential function. The inverse of y equals the natural log of x is called the natural exponential function. And it is denoted by f inverse of x equals e to the x. That is, y equals e to the x if and only if x is equal to the natural log of y. So it's actually defined in an inverse relationship way. It's kind of an interesting way of doing that because probably if you've seen this function before, and I'm sure you have somewhere, it wasn't presented that way. It was probably presented in reverse. Where in the world did e to the x come from? Well, it just sort of appeared out of nowhere, and then we introduced natural log as the inverse of that later on. And this book is using the alternate approach. And if you'll remember, the way that we introduced natural log was as a sort of an answer to the question of what's the antiderivative of 1 over x as well, right? So kind of a different way of thinking about it. Now, in order to work with exponentials, there are occasions when it's very nice to work with or to think about the properties that come into play with exponentials. So the next slide's got a lot of writing for you guys on it. These are the 6 basic exponential properties. I'll write a couple more down here in a minute just as reminders. So if you have a to the m and a to the n, you add the exponents. You don't change the base. It's not 2a or a times a or anything like that. The base is still the same. And then if you have the quotient, you're dividing a to the m over a to the m in, you subtract the exponents. An exponent raised to an exponent is a multiplication of those exponents together, m times n. On number 4, if you have a product AB and it's raised to the power of m, kind of has this sort of a distributive feel to it. We don't call it that, but it kind of feels the same way. It's a to the m and b to the m. 5 is almost the same thing, but it's with division of a and b, so we have a to the m over b to the m. And number 6 talks about what happens when the exponent's negative. In particular, it takes whatever is inside those parentheses and it flips it, does the reciprocal or the multiplicative inverse, and then it applies the exponent of m. Now, we could go through where in the world all of these come from, and they aren't terribly difficult features or anything like that. You've probably seen some of the proofs, if you will, of these at some point or another. If you are curious and you want to ask me, like, why in the world does 1 and 3 work the way that they work, we can talk about it after class, but those are really algebra issues, not really calculus issues, so I don't want to go too far down that rabbit hole. There are a couple others that you should be aware of because when they come into play, it's handy to remember them. If you have the exponent of -1, what happens? I know that's sort of just a specific case of number 6, but do you remember what happens when it's just plain old the exponent of -1? Yeah, it's just 1 over the value, right? So it is the reciprocal, but just keep in mind, and we've encountered that already once this semester. The other one we haven't encountered is what happens when the exponent is 0. Yeah, the variable or the base to the exponent equals 1, no matter what that base value is. We do restrict all of these to having bases that are non-zero, so we're not talking about a or b actually being the value of 0 in these cases. Weird things happen when zeros get involved, and obviously if there's zeros in denominators, that's not okay anyway. But we're looking at values here for a that have real numbers, but they're non-zero. Okay? Any questions or anything about these before we move on? Okay. So we're going to start again, just like we have in the other sections, in looking at sort of all of these things from an algebra point of view, the things we did in algebra with exponentials. And then we will move into using the differentiation and integration components of calculus on them. Okay? So you guys tell me, what are we going to do to solve for x in this equation? Add 6. You bet. All right, so I'm left with 3 e to the x on the left. I have 14 on the right. What's next? Right, I will divide by 3. So now I have e to the x on the left, and I have 14/3 on the right. Do you remember what you do next? Yeah, the problem, of course, is that we need that exponent x, which is where our variable is, not in the exponent. And there's a couple of ways to think about doing it. One way is to simply recognize that I'm allowed to take a natural log of both sides of a function. It's kind of like taking a square root of both sides of a function. I didn't mean either. I meant 14/3 there. On the left-hand side, then, properties of exponents say that that exponent of the x can come down in front, and I have x natural log of e. And why is that friendly? Yeah, the natural log of e is actually 1. So this gives me just x on the left, because this quantity right here is the value 1. And I've got the exact answer, which is natural log of 14/3. So I expect to see natural log 14/3 if you were writing this out on a quiz or on a test. That's the exact answer. And then the expectation would be to approximate that to 3 decimal places. So if you round that to 3 decimal places, what do you get? 1.540. Okay, so for computational purposes, you're going to need your calculator for some of these problems. Is that good? Did everybody get that on your calculator? Excellent. Okay, let's take a look at a couple more. Or, I'm sorry, one more. All right, this one is actually a natural log problem. And now, again, the problem, if you will, is that the variable is inside of the log. So somehow we've got to sort of pull it out, get it out from the outside. So what in the world would we want to do to solve this for x? Yeah, so it's, again, kind of like that taking the natural log of both sides. I'm allowed, if the natural log of 4x is equal to 1, which they're telling me that it is, to make e the base on each side and raise the e to each of the powers that are given. Why is that helpful? Well, that's helpful because one of our properties of exponents says that the e raised to the natural log are inverse operations. So in some sense, and again, this is a loose way of saying this, they cancel out. But they really do, you know, like multiply by 4, divide by 4 kind of things. They invert one another. So we have left on the left the 4x, and I have e, or e to the 1, on the right. Okay. What would I do then to get this x alone? I would take and divide by 4, right? So I have e over 4. Again, that's the exact answer, e over 4. Your calculator will give you a decimal approximation next, and we're using 3 decimal places on these directions. So what is the approximate value of this? Thank you, 0.680. So I would want to see that you have both of these answers written down if you were doing this and it's something that you're going to write and turn in. There's a couple places in your calculator. It depends on what you're wanting to do with it. If you're actually going to raise it to a power, it's on the ln button. Mm-hmm. So you can hit the alpha key and then ln. I didn't hit that right. Let me try that again. Is it not alpha? It's second. Sorry. That's what happens when you look at it upside down. The second key, there's E. This automatically puts an exponent in there, so put the number 1.
Okay.
Okay, and then you can hit enter, or you can hit the divide by 4 on the same screen. There you go.
Awesome.
And rounded to 3 decimal places is going to give me 6.8 on that. Okay, is everybody else able to find E? We're good to go? Excellent. Okay, this is one place I wanted to show a graph. So what we're going to do is we're going to just take a look at the graph first of e to the x. And then we're going to make some observations, much like we did with the natural log graph, about the graph of e to the x. Okay, go ahead and put in e to the x. So you can use that same second natural log feature, and then e to the x here. And we'll use the regular zoom window, so zoom 6, it's your standard window. The graph looks something like that. That should be a fairly familiar graph. You have seen it before. Maybe you haven't worked with it in a while, but it is a fairly familiar graph. So taking a look and thinking about that, we're going to identify some features of that graph. So it should look something like this. It almost looks on your calculator screen like it sort of hits the x-axis or it stops. It doesn't. It just gets very, very close. So the first thing to recognize is that there is a y-intercept at 0, 1. So this location right over here where it is crossing is at 0, 1. There is no x-intercept, and the reason, of course, there is no x-intercept is because it has a horizontal asymptote at y equals 0. This graph, much like the natural log graph, increases without bound. So what that means is if you go to the right forever, that is the limit as x approaches infinity, the y value increases forever. Y approaches infinity. So the limit of e to the x as x approaches infinity is infinity. The domain is negative infinity to infinity, and the range is 0 to infinity. The graph is continuous, 1 to 1, and concave up. Okay. I know you guys have several things to write down, but once you do have them all written in, what I'd like for you to do, if you have it with you, is to pull out your notes from section 1, 5.1, and I want you to compare this list to the list that you saw in 5.1. So in 5.1, we had the graph of y equals ln of x, the natural log graph, right? And if you take a look at these features, you should almost feel like I've written all of these down before. Not exactly like this, but very close. Like on the first one, our y-intercept of this graph is at 0, 1. Well, on the natural log graph, we had an x-intercept at 1, 0. On this graph, we have no x-intercept. On that other graph, we had no y-intercept. On this graph, there was a horizontal asymptote at y equals 0. On the other one, there was a vertical asymptote at x equals 0. It increases without bound. Both of them looked exactly the same on that one. The domain and range, what do you notice about the domain and range of this one compared to the other graph? Yeah, they switch, right? They just switched, and they switched because they're inverses. You're right. Continuous and 1 to 1, those features are the same, and then the concavity is flipped. Now, if you were to graph, and go ahead and take your calculator and do it just because you have it out there anyway. If you were to graph the other graph on here, it would look like this. And from what we did last time, you know that if you were then to draw the line y equal x in, it would look like this. And visually, what do you see? Mirror images, right? You see that inverse relationship going on. And of course, that's why the features look like mirror images, but in some cases switched from each other, like the domain and the range. We switched x and y. Domain and range would switch. That should be sort of expected to happen. Okay, one thing else that I want to remind you of before we move too much further forward is what transformations look like with a graph like this, because they're slightly different. So if you had the graph of y equals e to the x, these are the 4 locations where different numbers could be, a, b, c, and d, and alter the image of your graph. If you have a number multiplied in front of e, that's called a vertical stretch or a vertical shrink. It's a stretch if the a value is bigger than 1. It's a shrink if it's between 0 and 1. We'll talk about negatives here in a second. If you have the b that's multiplied by the x in the exponent, that's a horizontal stretch or shrink. Now notice the stretch is the 0 to 1 and the shrink is the greater than 1. It sort of switches the way we're defining it because of the way that those stretches actually affect the graph. C, that is a value that's added or subtracted to the exponent. If that value is bigger than 1, it shifts it left, and if it's less than, not bigger than 1, excuse me, bigger than 0, it shifts it left. And if it's smaller than 0, it shifts it right. And then if you add anything on the end, that plus d, if that value is bigger than 0, it shifts it up, and if it's less than 0, it shifts it down. All right, so a couple of things about this before I talk about the negatives on the letters A and B. Whenever I think about stretches and shrinks and shifts and so forth, I think about things on the inside as they're affecting x and on the outside as they're affecting y. So you'll notice everything that's in the exponent up there and on the top, that's affecting the x values. So B and C affect the x values. Well, x values are horizontal values, okay? So the b value is affecting it horizontally because it's grouped inside with x. It's a horizontal stretch or shrink. It's moving it left or right, that c value, because it's inside with x. It's affecting the x values. The a and the d are outside of where the x values are. Hence, they're actually affecting the outcome, the y value that's on the other side of the equation. Okay, so the a value will be a vertical stretch or shrink because it affects the y values in the function. And the d on the end is a shift up and down because it's affecting the y values of the function. Now, looking back on a and b, it doesn't say what happens if the graph had a negative in those locations. That is, what happens if a is actually less than 0 or if b is actually less than 0. So what happens when you have those negatives involved instead? Do you remember? Okay, let's try one. Grab your calculator just for fun. You've already got the equation of y equals e to the x in there. Change it so it says y equals e to the negative x. Let's just put a negative up in the exponent with x. Y equals e to the negative x. So this would be like making the letter b in this equation up here, negative. What happened? It flipped it. We usually call it a reflection, and it reflects it in this graph how? Across the y-axis, right? It reflects it like this, right? It reflects it over the y-axis. So if you have a negative in the exponent, it's going to be a reflection across the y-axis. Now, take the negative out of the exponent and put the negative in the front instead. What do you think it's going to do this time? Yes. And again, the reason it does that is because if it's a negative inside, it's affecting the x values, right? And if it's a negative on the outside, it's affecting the y values, so it flips it down. Okay, so it's reflections. It doesn't actually change the shrinking or the stretching. The negative part doesn't. It changes the location of the graph around one of the axes, depending on where you put the negative. Okay, so these are some basic ideas and remembrances as we're taking a look at graphs and so forth. We're not going to do a whole lot with those things, but they do come up from time to time. Now, the derivative is the best derivative you will ever encounter. He's the most friendly because he is himself. The derivative of e to the x is e to the x. It's a fantastic feature. And in fact, for those of you who had me for Calc 1, when we looked at the graphs and then we graphed the derivative graph, we actually used this as one of our situational ones that we used because he's so friendly. And it happens so infrequently that when it does, it's almost like, did I do something wrong on a graph? You're like, wait a minute, I just graphed that, and it's the exact same graph for the derivative. That shouldn't happen, and in most cases it doesn't, but it does for e to the x. So we're going to take some examples and practice with them. You do have an e to the negative x in this one. You also have an x squared. What is the overarching rule that you're going to be using on this derivative as you take it? What rule are you going to have to use? Property. You will have a chain rule, but bigger than that. There's something else going on too. Product rule, right? This piece and this piece are multiplied. So we have a product rule. So you can do the product rule in either order. I usually do the product rule where I write the first piece down. Some of you probably learned that you take the derivative of the first piece. It doesn't matter. It's okay either way. What then, if I've written this down, will the derivative of e to the negative x be? So Kay mentioned, and she's right, there's a chain rule involved, right? Because it's not just e to the x. It's e to something else. So the chain rule says we take the derivative of the outside, that is, we take the derivative of e to the power. Well, e to the power is e to the power. That's what our new derivative rule is that we just encountered, right? But then the chain rule comes into play, which says, okay, but I need to take the derivative of the exponent of the power. And what is the derivative of negative x? Negative 1. Exactly. Product rule says I add. And since I took the derivative of the second one last time, I'm going to take the derivative of the first one this time. So what's the derivative of x squared? 2x. And then I simply rewrite the next piece. Now, I don't remember when it is, but at some point in the near future, you're going to take a quiz. It's called a basic skills quiz or a gateway quiz. I don't remember what I called it in your stuff, but when is it? It's a week from today. So September 13th, a week from today. If you were doing that quiz, this would be perfectly acceptable for your answer. You don't have to keep going. You just leave it in its messiness right there. Now, in terms of cleaning this up and simplifying this, you might ask yourself, well, if I don't get to leave it right there, what do I need to do? Well, the first thing to notice is that you have a negative out here in front. So I'm just going to reorganize a little bit what I have. So I have a negative x squared. I have e to the negative x. And I have plus 2x e to the negative x. So not a lot of rewriting in that particular step. I'm fine if you leave it like that. I'm okay with that. If you were using this, however, to do something with it, so what might you do with it? Well, you might set something equal to 0. You might need to take a second derivative. If you were actually working with this beyond this point in the problem, there are a couple features that you should be aware of that would be helpful to do. In particular, it would be helpful to notice the pieces that match. So both of these have an e to the negative x in them, right? So often what you will see sort of if you were to look in the back of the book on this problem, say, or something like that, or if WebAssign freaks out and is like, simplify it or something like that, is that they will probably factor out the e to the negative x. You'll notice I left a space in front of mine because they'll probably factor something else out as well. Any idea what else they might factor out? An x. They probably will. And then Nate sort of did something in the air where he switched it around. And they probably would do that too. They probably wouldn't leave it as negative x at the beginning. They probably would rewrite this. So if you're identifying the pieces that we haven't sort of dealt with, there's a 2 right here, and there's a negative here, and part of that x squared, namely the x part of it, is left. So you probably would see them put the 2 at the beginning, not because it matters, but just because it's kind of friendlier to write this as 2 minus x. Or negative x plus 2. So let me re-say one more time what I just said before. I'm okay with you leaving it there. There's nothing wrong with that. The reason that you are seeing me do this right now is because for practical purposes later on, it will be helpful for us to have seen this factoring out business once before, okay? Okay, let's try another one. This one's even more fun. Because what do you have here? We have a quotient rule. All right, quotient rule. And inside of the quotient rule, there's also the chain rule, right? Because the exponent doesn't just have x in it, it's 2x. All right, so quotient rule. I don't think we've done a quotient rule in a little while. So, at least together in class. How does quotient rule start? It's like the product rule, right? Do we start with taking the derivative of the top or taking the derivative of the bottom? Which one stays the same? Which one changes?
Bottom, top.
Yep, the bottom first. And then the derivative of the top. Okay, so the derivative of the top, what is the derivative of e to the 2x? Right, so it's e to the 2x because that's the derivative of e to a function, and the derivative of 2x is 2. So if you recognize that soon enough, you're welcome to put the 2 in front, or if you recognize it later on, you put the 2 at the back, it doesn't matter. So it's 2e to the 2x. Unlike the product rule where I have addition, I use subtraction with the quotient rule. And I want to do it the opposite way. Now, what is the derivative of the denominator? What is the derivative of e to the 2x plus 1? It's actually 2e to the 2x, right? And then I have the original of the numerator, which was e to the 2x. And all of this is over what? The denominator squared. And typically speaking, we don't multiply that denominator out. It'd be few and far between when you would ever actually want to multiply that squaring of that denominator out. So we won't be multiplying that out on this particular problem. We are going to clean up the numerator though. So again, if you were doing the gateway quiz next week, you would leave the numerator. You'd leave that problem just like we already did it. We would be done. Okay? But there's definitely some cleanup involved in what we can do. So I've got a 2e to what power? What happens when I multiply e to the 2x times e to the 2x? You add them. That's why we looked at those original properties of exponents at the very beginning today. You add the exponents. So if I add 2x and 2x, I get 4x. And then I have plus, and now I have, so I did this piece. I have this piece to do. So we have multiply by 1, so this is just 2e to the 2x. And then I have minus. Now I've got 2e to the 2x times e to the 2x, which feels like something we already did. Right? 2e to the 4x, right? Over e to the 2x plus 1 squared. And then what wonderful thing happens? Yeah. Does add to 0. I mean, maybe it's not wonderful. That might have been a strong word for it, but it's friendly. So we end up with simply 2e to the 2x on top and e to the 2x plus 1 quantity squared on bottom. Any questions on that one? Okay. So I warned you, sometimes you have to take the second derivative as well. So we're going to do that for this particular one. Take the second derivative of the function, and of course when you take the second derivative it means you really take the first derivative and the second derivative. So we have a product rule much like the example 2a above. So as we're looking at this derivative, somebody walk me through what you would have. Okay, I'll do the hard part and get us started. 3 plus 2x. Now what? Yeah, e to the negative 3x times negative 3. So I'm going to write it in the other order, Evans, and put my negative 3 at the beginning. So negative 3e to the negative 3x. Yeah.
Why in that case does the x not come down also?
It's not coming down at all. It's a chain rule, so what we're doing is we're taking the derivative of e to the exponent, and e to the exponent's derivative is e to the exponent. Then we take the derivative of the exponent.
Okay.
Yes. The tricky thing here is to keep in mind that the power rule that you know and love is not the rule that's going on in these particular problems. And the reason is because the power rule has the base as an exponent, and here our base is a constant. That's the difference. You're welcome. Addition, right? Now I need the derivative of 3 plus 2x. 2, right? And I will rewrite the next piece as is. Okay, that's all the calculus that there is in this particular problem. But we will want to clean this up, and in this case we really want to clean it up because we have to keep going. So we're going to distribute and simplify what we can. So I have negative 3 times the 3, so I have negative 9 e to the negative 3x. And then I have minus 6x e to the negative 3x. And I have plus 2e to the negative 3x. Are there any of those that I can combine? Right, the first one and the last one. These match because they have the same components variable-wise, the e to the negative 3x, and that's all they have. So I actually have negative 7e to the negative 3x minus 6x e to the negative 3x. Okay, you could take the second derivative from that spot. It would be okay. It wouldn't be like the worst thing you could possibly do on this particular problem. However, I think it will be friendlier if we factor out the e to the negative 3x first. Okay, so my suggestion will be to take that piece out because it will save you maybe 1 or 2 steps at least later on. So if I factor that out, I have e to the negative 3x times negative 7 minus 6x. That's the first derivative in its sort of condensed form. And our goal is to take the second derivative. And the nice thing is that if you notice, the second derivative then will almost feel like doing the first derivative again because we've factored it in such a way that we see that resemblance. So I will write the first piece first. And then I need the derivative of negative 7 minus 6x, which would be what? Negative 6. Plus, now I need the derivative of e to the negative 3x, which we've done before. What's the derivative of e to the negative 3x? Right, e to the negative 3x times negative 3. So I'm going to write negative 3e to the negative 3x. And then that will be multiplied by the original of the other piece, so negative 7 minus 6x. Again, that's all the calculus that's involved in the particular problem, but we're going to clean it up. So now I have negative 6e to the negative 3x, and then I'm going to distribute. So I have negative 3 and negative 7.
Why not just take it out?
You could. Do you want to do it that way? Okay, that's fine. All right, so Evan suggested instead of actually distributing. Okay, so if we do that, Evan, we need to change my negative 6 at the beginning, right? Is that what you're meaning?
Yeah.
Like this? Okay, so Evan's suggestion is for us to factor out the piece that they have in common, this piece, which works great. So I have negative 6, and then I have negative 7. Okay, I think I'm going to have to do a positive 7 at the very least, correct? Because this negative will at least get distributed.
21.
Yeah, so we're going to have positive 21 at the negative and the 3. And then a positive 3 times 6, which would be 18x. So we factored out the e to the negative 3x, and we distributed to the negative 3 coefficient at the same time. And again, if you don't like that, that's okay. You can do it in the other order, which is where I was headed before. So it's e to the negative 3x times what? 15 plus 18x. And that's actually the second derivative that we were looking for. If you wanted to, could you factor a number out of the 15 and the 18? Sure, you could pull the 3 out if you'd like to. I'm not going to worry with it, but we could. All right, so that's derivatives. Now we're going to do antiderivatives. So if the derivative of e to the x is e to the x, then the antiderivative would be as well, right? I told you it was friendly. So the antiderivative of e to the x, that is that capital F of x is e to the x, you still have to remember the plus c, so you don't get away from that. But you do have an antiderivative that is pretty much itself. So we're going to do a couple now, because that's what we should do, right? Practice. All right. Taking a look at this one, it's not just e to the x, right? So when we saw it for derivatives, Kay mentioned we had a chain rule, right? So when we see this for antiderivatives, what do we mention or notice that we have to do? Yeah. How do we deal with it though? When there's because we don't have a chain rule for these u substitution. Very good. So we're going to do a u substitution. The u will be what? 1 minus 3x. You got it. Okay, then what is the derivative of 1 minus 3x? Negative 3, and then it's the dx, right? Okay, there's not a negative 3 in the particular problem, right, down by the dx. So we have to divide this. This is negative 1/3 du is equal to dx. So as we are changing this over here, I usually put the negative 1/3 in front, as you guys are aware. You have your antiderivative. The e is still in the problem. Don't lose it. And the u is the exponent on e. And then I have the dx at the beginning, or at the end, replaced by the negative 1/3 at the beginning, and the du at the end. Right? So this piece gets replaced by this and this combined. All right, so what is the antiderivative then of e to the u? E to the u plus my c. And then the last thing you would need to do is what?
Replace u with the 1 minus 3x.
Yes, thank you, Abby. So we have 1 minus 3x as our exponent on e plus the c at the end. It's okay? Okay, the next one's more fun. Look at that. Wow. Look at all those x's and e to the x's and things like that. Okay. We encountered something that looked similar to this in the last couple of sections of work. The issue that we ran into was that if you have addition and subtraction in the denominator, it makes it terribly difficult to work with the numerator. Do you remember the method we used to get rid of that addition and subtraction in the denominator? We did u substitution with the denominator. Okay? The denominator being pluses and minuses is the problem. That's really the problem here. Okay? So we're going to let our denominator be u. Okay, what's the derivative of e to the x? It's e to the x. And I have minus. Now what's the derivative of e to the negative x? E to the negative x times negative 1. Right. So it's going to be a positive. Like this, right? So this is going to be e to the x plus e to the negative x. And what do you notice? It's exactly what's on top. Won't equal 1. But what will happen is that the piece that I just highlighted and this one will all get replaced by du. Right? Because this expression is equal to du. Everything that's highlighted on the board right now are equal to one another.
If it was just my curiosity, if
Mm-hmm.
you were multiplying e to the raised to the x times e to the negative x, wouldn't that just come to 1? Put the e to the x on top and you can bring the e to the x.
Yeah, if you were multiplying e to the x by e to the negative x, you would end up with the value 1. Yes, that's correct. They're multiplicative inverses of each other. That's true. Yeah. Huh?
I like that word.
You like the word multiplicative inverse? Why? Because it's fun to say? It's fun to say. It is. All right. We've got an integral. The part that's in red is du. I still put my du at the back and my 1 on top. If you want to put the du on top, you'll see that done a lot of times too. It doesn't matter to me. But what's going on the bottom of your fraction here? It's u. Right? Okay. Now, you've seen this before. What's the antiderivative of 1 over u? Natural log of the absolute value of u, actually, right? Yeah, that's going to catch some of you if you're not careful on those quizzes, right? This is the antiderivative quiz. It's not the first one. But something cool is about to happen, so hold tight. What was u?
U is the e to the x minus e to the negative x.
Okay. Like this. Now you have to be careful, okay? If we had just had, if we'd had, let's say for instance this had said the natural log of e to the x plus e to the negative x. It's not what it says, okay? But let's say it were a plus sign in between them. We wouldn't actually need the absolute values, okay? Because these quantities are both positive. E to the x is positive, e to the negative x is positive. They're both positive. The problem is that it is possible to take two positive numbers and subtract them and get a negative, right? Like think 3 minus 5. Okay, so I do need the absolute values here, but if it were addition, I wouldn't necessarily need them, because if I added two positives, that will be positive. Okay, so we are done on that one then. Okay. Okay, we have one more. We have one more. We'll look at the quizzes next time, I promise. Okay, definite integral. What in the world is meant by definite as opposed to indefinite? It's not that it goes to infinity, it's exactly. It's that we don't know where it starts and stops. Okay, so we don't have like those limits. Definite integrals have limits of integration. So this one you see is 0 and a square root 2, right? And it does mean, like you had mentioned too, there's no plus c's, right? There's no plus c's on these because we actually have limits that we're going to plug in for the endpoint, the top and the bottom endpoint. Okay, taking a look at this one. This problem looks like x times e to the negative x squared over 2. It looks like there's multiplication in it, correct? And we do not have a product rule for antiderivatives, correct? Okay, so don't try to do something product-wise because there's nothing for that with antiderivatives. And we're kind of like grasping at straws because you don't really have a lot of tools yet to do this, but there's one tool that you have that we keep using over and over and over again, and it's called u substitution. So right now, when in doubt, u substitution. What will the u be? Okay, so it's not going to be the e. Yeah, we want it to be the part with the variable in it, and the variable in it here has the is the exponent. It's not written very well, but we have negative x squared over 2. And you might be asking yourself, well, could I ignore the negative? Could I leave the negative? You could. It wouldn't hurt anything, but I tend to like to make the u substitution as all-encompassing as I can because it means that the antiderivative later is cleaner and simpler. So I tend to deal with the negatives right here. All right, so there's u. What would du be? Negative what? Negative x. Does everybody see that? So the derivative of the x squared is 2x. The 2x is currently divided by 2, so the 2's would cancel. The negative is still involved in the problem, so I have negative x dx. Now that's not quite exactly what I have in my original problem, but it's awfully close. By what does it differ? The negative, right? So if we'd left the negative in it, we wouldn't have the negative to deal with here now, but it's not bad. All it means is that I'm going to divide the negative to the other side. So I'm going to have negative du is equal to x dx. So when I replace the x and the dx, I will replace it with a negative on the outside and a du at the end. Okay, so the parts that I circled in red are now replaced, or they're changed, substituted for. What will remain inside? The e to the u. And my preference personally is that I don't put the limits of integration on. I will change this back into the x's here in a minute, and then I can put my limits of integration of the 0 and the square root of 2 back on. What you don't want is the 0 and the square root of 2 on the limits right here, because the limits right here would apply to u, and the 0 and the square root of 2 applied to x. Is everybody okay with that? Okay, so my preference is just to leave them off for now because I don't want to mess with changing them. What's the antiderivative? Well, there's a negative here. I'll continue with it. What's the antiderivative of e to the u? E to the u. Isn't that nice? And we know what u is. It is negative x squared over 2. And now that it's back in terms of x's, I will put the limits of integration, that is square root of 2 and 0, back into the problem. Definite integrals are a little bit more work than indefinite integrals, right? The ones we were just doing before, right? Because I have to continue in this particular problem now with plugging in values. So what happens when I plug in square root of 2? Well, I'm going to have square root of 2 squared, which is 2, divided by 2, which is 1, and I've got the negative at the beginning. So this is negative e to the negative 1. That's what that simplifies to being right now. What happens when I plug in 0? What is 0 squared? 0. Divided by 2? And then when you put the negative on it, it's still 0. So then this is minus e to the 0. All right, so typically speaking, you wouldn't leave it like this because we can write this, number 1, with the e to the 0 written as 1. But also the negative exponents are usually sort of frowned upon in mathematics. So what would we rewrite the first piece to be? Negative 1 over e, and the second one would be minus 1. Oh, I'm sorry. Is it plus 1? Oh, because I left my negative off here. You're right. Let me move this over and put that back in. It was minus, and then it was the negative from inside there. Yeah, too many negatives, or not enough actually. So I have a plus there, yes. So you might see it written that way. That's totally fine. You might also see 1 minus 1 over e written. Or another option, just if you were sort of comparing notes with someone else or whatever, is that you, and I'm not saying you should do this, but you could get a common denominator, and this would be then written as e minus 1 over e, because the 1 at the beginning would be written as e over e. So those would be 3 different versions of exactly the same thing. Well, you mean to simplify, like to get a decimal approximation? It would be a possibility, sure. You could be asked for a decimal approximation for this. Truly, most of the time, we don't decimal approximate anything, but occasionally there are times when we will, application problems, that sort of thing.